Recording is rolling. All right, now we're at the last few minutes of class. I've been walking around. A bunch of guys are correctly getting the coefficient of friction. And I have had a poster for this the whole time. Turntable friction. Here's the lab exactly that you guys are doing. So let's go over the step by step because a lot of you guys got the whole thing, which is awesome. So I have this turntable. It is turning. Look, I got an angular velocity right here. Omega, angular velocity. It's turning. Right. I got this mass. Maybe that could be this guy right here, setting some radial distance from the center. Got that? Okay. And what would be holding it on there is a friction force. So the full free body diagram looks like this. Weight down, normal force up, which exactly balances that out. And I got the friction force acting as the centripetal force. Whoops, I didn't mean to give that away. I'm so sorry. I was going to ask you guys. This friction force is acting as a what kind of force? And you guys would have said centripetal. And that's the first step in this process. That's like the first domino, and everything else is going to chain of dominoes after this. Okay, so the friction force is providing the centripetal force. Guys, do you guys know a formula for centripetal force? Or sorry, let's start with friction force. Friction force. What's the formula? Coefficient of friction times the normal force. You guys remember that? Because you guys did that lab a few weeks ago. So that could look like that right there. Coefficient of friction times the normal force. Right? Do you guys know an expression? Actually, you guys know two different formulas for centripetal force. I showed you guys two different ones. One of them you got from a lab, and one of them I have a poster for called O'Neill's cylinder. All right, so let's look at them one at a time. Here's centripetal force straight from your lab, mv squared over r. Okay? Now you can substitute in, you guys see this v right here? Omega times r, and that leads straight to this O'Neill cylinder poster. Hey, remember O'Neill cylinder right here? Here's also centripetal type force, but it's in terms of angular speed instead of linear speed. So m omega squared times r, right? Which is probably more applicable to this turntable lab. You could do that, right? And that's exactly the next line right here, m omega squared r. Is there another two? Right. Hey, why do I have an inequality? Why is it an inequality? Okay, let's think about it this way. If we're talking about static friction, go back to this turntable. If I spin it really slow, then do you think it's only a tiny, tiny force to keep it on? Yeah, and I spin it kind of medium. Now this friction force gets a little bigger. Then spin a little faster, a little bigger. Spin a little faster, a little bigger. Right? Now at some point it won't be able to hold it on anymore. You spin it too fast, which is exactly the point that you guys are interested in your lab. Right? So if you're maxing out the static friction, you're allowed to change this inequality to just a plain equal sign. So for the rest of this lab, rest of this poster, just imagine this is equals, and that applies to your lab, right? Right. Oh, next line. What am I about to be substituting in place of normal force? I'm going to substitute what? What's normal force equal to? mg, exactly. Bing, bing, bing. That's this line right here. Look at that. Same thing. I just substituted an mg. And now, what cancels on both sides? Goes away. This mass right here. So turns out maybe you just had this stuck to the table. Maybe you had this stuck to the table and you have this guy on top of it. Would that make any difference at all? No, because it cancels out. Cancels out right there. Right. So just do a little algebra shuffle and you get exactly the answer, which again, a lot of guys I saw got that exactly, which is awesome. You guys plugged in the numbers, you guys did the correct calculations, made correct measurements, calculations, did the whole thing, got the answer. And what were you guys getting for a coefficient of friction about? I saw some of you guys' papers got maybe like 0.2. There was a range of values, but I remember that one coming up, which is probably pretty accurate. Right? So there you go. Just make this an equal sign. You got it. Here's the angular speed. And because what's the units for angular speed again? Is it revolutions per minute? Radians per second. Right, so you got radians per second here. You got to square that. Multiply by radial location from the center. And then, oh, hey, remember I was saying earlier today, I bet if you did this on Mars, you'd have to spin it at a different rate to make it spin off. Gravity field matters. Okay. Make sure the units are consistent here to here. As if you did gravity in meters per second squared, your radius was measured in what? Meters. If you use centimeters for radius, what did you use for gravity? Centimeters per second squared, like 980 maybe, something like that. All right, there you go. You get coefficient of friction.